My name is Nico Lang and I'll be presenting our work from coarse to fine-grained open set recognition. Let's start by recalling the open set recognition task. At train time, we might have access to a set of known categories, in this example two butterfly species, which is often referred to as the closed set categories. Once we train the classifier on this data and deploy it in the wild, we might encounter both familiar and novel categories. In this task, we want to model a score that ranks the test data from familiar to novel, which is useful in both robustness but also discovery applications. Recently, Weiss et al. Has shown that the open set recognition research has a little problem. The issue is that OSR performance correlates strongly with closed set accuracy, which makes it hard to evaluate the progress in OSR research. They've also shown how to construct easy and hard OSR splits based on attributes. We build on this work and ask what makes OSR a hard problem. We study three underlying confounders, namely semantic similarity, label granularity, and hierarchical representations. We make use of existing taxonomies as a proxy for semantic similarity. We identify large-scale natural world image collections like the one from iNaturalist as an ideal data source to study open set recognition in fine-grained settings. Specifically, the INET 2021 dataset by Van Horn et al. Contains 10,000 species and 2.7 million images distributed around the globe. Based on this dataset, we construct two open set recognition splits, one for aves, birds, and one for insects. For example, we hold out 745 bird species as the training data, the closed set, and organize the remaining species into 7 open set splits with increasing semantic shift, measured as hop distance. Here are 3 examples from the aves split. So on the left, we see 3 categories from the closed set data, with corresponding examples from the open set splits. We see, when we go from left to the right, how the classes are semantically more different and visually more different. The hops from 1 to 4 are still within the supercategory bird, but when we go beyond that, we might encounter other animals, plants, or fungi. Here are 3 examples for the insect data. We use this dataset to evaluate 3 commonly used scoring methods and find that there is substantial drop from the large semantic shifts to the small semantic shifts, so when going from 7 hop to 1 hop. We also find that the choice of scoring method depends on the semantic shift. For instance, in the 1 hop setting, the maximum logic score performs best, while in the 7 hop setting, the ensemble disagreement score performs best. We study different training strategies. First of all, we look at the role of supervision granularity when we train a separate model for every granularity in the hierarchy. Then we look at the role of hierarchical representations. First, we study a hierarchy supportive method where we train a single encoder with multiple classifier heads, one for each granularity, which should encourage hierarchical representations. Second, we propose a hierarchy-adversarial method that aims to discourage hierarchical representations. So here we want to learn an encoder that's still able to classify at the finest grained level, but should maximize the cross-entropy for coarser classifiers. To implement this min-max problem, we make use of the gradient reversal layer originally suggested for unsupervised domain adaptation. Let's have a look at the role of supervision granularity. The baseline at 0 is the performance of the models that are trained and tested at the same granularity, while the bars show the models that are trained on finer grained labels and then pooled to the coarser granularity for evaluation. We find that overly fine-grained supervision improves both open set and closed set recognition, which could be explained by the correlation observed by Weiss et al. When we look at the hierarchical representation, we first study the weight of the hierarchy-adversarial gradient. So in the left panel, when we increase the weight of the adversarial gradient, we first see how the open set performance goes up, while the closed set accuracy goes down immediately. This contradicts the observation by Weiss et al. However, when we look at open set distance with large semantic shifts, the hierarchy-adversarial approach deteriorates performance. Thanks for watching.